basis of this course. It's all active voice. Anyways, I'll talk a little bit about protecting yourself from plagiarism and some of the more egregious examples I've seen of people copying our projects. But I'll do that another day. What I want to talk about today again is Lab 4. And first question, so last time we zipped right through control theory in 50 minutes. So the first question is, what questions do you have about that? Then if you don't have any questions, yes?
Can I just ask?
Have at it.
So like, is there any other way of tuning PID besides like going like trying just different numbers?
Yes. Some of them actually work. So you can easily Google tuning PID algorithms, or you can go back to last year's. Did you know that last year's labs are all online? So if we go to old lab exercises, all the way back to 1997. So the motor controller from last year was somewhat simpler and had a description of how to, you could look at PID tuning, the Siegler-Nichols method, and optimum setting for automatic controllers, and a critique about why this is a waste of time. So you could go to last year's Lab 4 and take a look if you want. Or if you want to have a good laugh, go back and look at 1997. So but I will tell you that the trial and error tuning is going to be the least of your problem in getting this running. What other questions? I'm going to talk more about the scaling to the PWM and then go back and talk about the command loop again if you want. But the first thing you need to do is talk about how to set up a timer for PWM. Set up an output compare unit in a timer. And there's an example down here in the code. This is a fairly old example, so it's not wonderful. It also does a bunch of stuff. It makes a bunch of pulse trains. Some are out PWM, some are not. It then times the pulse trains. But there's just 2 lines of code you need from this example. The first is, call it 3, because you have to turn on a timer to control the PWM. You're going to set a generate period which is equal to the compute period of your algorithm, which I'm suggesting should be 1 millisecond. In other words, you want the interrupt service routine to run at a kilohertz. So the generation period is going to be, what numerically? Huh? 40,000 if you're running at 40 megahertz, right. So the generate period will probably be about 40,000. Then you're going to open an output compare unit. What an output compare unit does is to watch the timer time out and produce a pulse train based on the timeout. And if you open the output compare with timer 2 as the source and put it in PWM mode, oh, fault pin disable. What in the heck does that mean? Well, it turns out that the designers of the chip know that people tend to use PWM to control motors. And if the motor, say, freezes, and so the current goes to near infinity, you'd like to know that. And the PWM fault pin will signal to the CPU that there's a motor problem if you have a sensor on the motor. So I'm disabling it because I don't think we're going to have that problem. And then you can put any numbers in here you want, because the very next thing you're going to do, the third line of code that you need, is up here, which says set the PWM output to PWM on time. That's all you have to do to set the PWM on time. So let's say we do that call and we set the PWM on time to 1. Then you're going to get a single cycle pulse out about every 40,000 cycles. Assuming that you have the timer 2 set up for a 1 millisecond interrupt service routine. So the average voltage, if you were to integrate over 1 millisecond, the average voltage is very low. It's about 1/40,000th of 3 volts output. On the other hand, if you set the PWM on time to 39,000, say, then you're going to see something that looks like this. In other words, the output of the PWM is going to be high most of the time, and so averaged over 1 cycle, the output is going to be very near 3.3 volts. You set it to 20,000, and you're going to get a 50% duty cycle square wave. So this is going to be the output that you feed through a resistor and into the opto-isolator LED. So you need to do 3 things. You need to, of course, have a timer running. You need to open an output compare unit, and you need to set the PWM on time. In this case, for you, this statement, this PWM on time set, is going to be in the interrupt service routine. So once a millisecond, you're going to change the PWM on time according to your control algorithm. Any questions on that? Yeah.
Where are we putting that the whole cycle is 40,000 hertz?
Where are you putting that? You're doing that by when you set up the timer.
Okay.
So the period of the timer is going to be 40,000.
Okay.
Because you want, if you're running the main clock at 40 megahertz and you want a 1 millisecond interrupt service routine, then you're going to be counting up to 40,000.
But when you open up the output compare unit, don't you pass in values in terms of the timer's period? So
It doesn't matter what you pass in when you open it up, because one interrupt later, you're going to change that value.
right, but when you're adjusting them, it's in terms of cycles of the timer that you're using, not in terms of cycles of the real clock.
It is in terms of, this is in CPU cycles.
The timer's period is in CPU cycles, but the output compare unit
Is in
timer cycles.
CPU cycles.
Your the example code has it be 500, whereas the timer is set up with.
My example has what?
Okay, so in your example code, your PWM on time is 500, which sounds like it's in terms of timer cycles, not CPU cycles.
CPU cycles.
Well, your timer is running at a much longer period than the CPU, so they're not the same.
The timer is timing out every 40,000 CPU cycles. The length of the pulse that you specify is in CPU cycles from 0 to 40,000.
Okay.
or whatever your timer is set at, but I think you're probably going to be using 40,000. Yes?
Actually, I have a question. So why are we using kilohertz as our PWM frequency while we're also using a kilohertz as our sort of signal, generation PID frequency?
So why use a kilohertz? Well,
Why not use a different one just in case?
you could, but why bother? First of all, the 4N35, the opto-isolator, has a bandwidth just a little bit bigger than a kilohertz. So if you were to run the computation faster than that, you would certainly have to use a separate PWM setting interrupt to choose a frequency below a kilohertz for this device. The switch is very fast. The transistor is not fast. And the reason it's not fast is that the phototransistor is not fast because it takes a while for charge to leak off of the base.
Okay, so when you open up the output compare, you pass the PWM on time twice. What does each of those do?
Technically, one is this edge, the other is this edge.
Okay,
You don't care about that. You just set the PWM on time.
wouldn't you want one to be the PWM on time and one to be the total length of the cycle minus the PWM on time?
I'm telling you, the only place you're going to set this that matters is when you set the PWM on time. Otherwise, mess with it.
I think I may be very confused on what it is that it's doing then, because if it's doing what I think it's doing, it matters.
It does not set the period.
Okay, so the open output compare function takes in configuration and then two values, which
Mhm.
you're passing a PWM on time for both of them.
Uh-huh.
What I would assume that does is one of them sets the on time, one of them sets the off time.
Yes, which you are immediately going to modify with the PWM set time call in the interrupt service routine.
Right, but don't you need the on time and the off time to sum to the period?
No! Well, actually, those are the absolute times. So it's not the duration, it is the point during the counter cycle that this happens. I'll take this offline and we can argue about it with regard to the hardware data sheet later, okay?
Okay.
All right. Anything else? So, as we talked about last time, you're going to compute some function which is going to be, so this PID algorithm is going to be some k proportional times the error in angle at time n plus some k derivative times error n minus error n minus 1 plus an integral term which is going to be something like ki times the sum of the errors. And I actually didn't use n minus 1 here to calculate the derivative, but rather 4, x equals 4. And I'll tell you why in a minute. The reason is, well, let's talk about units. Now we have to actually get down to units here and talk about the size of actual numerical values to decide what the the constants should be. And we know that we need an output between 0 and 40,000. We need the output to saturate at 0 and saturate at 40,000. So we're never going to go below 0. That's equivalent to not being able to turn the motor backwards. And the potentiometer, when held with the beam horizontally, should be set to about half of the maximum ADC value. The maximum ADC value is 1023, 10 bits. So we'll say that when this is horizontal, the angle is 500 ADC units. It's about half the range of the ADC. If that's true, then when the beam is hanging straight down, then the angle, well, all right, and as we go through 340 degrees, I believe it is, the ADC is going to go from 0 to 1023. So we can ask how much is 90 degrees, and it's something like, around 250 units. So when it's hanging straight down, we're going to have an ADC output of around 250 units. This is let's say now we turn the system on and the pendulum is hanging straight down. We'd like it to be horizontal. That's a big error. In fact, it's one of the biggest errors you can get in the system. It's 90 degrees. That would suggest that we want to turn the motor on full power so that it quickly goes to the 0 position. If we want to turn the motor on full power and the current error is now 250, 500 is the desired angle minus the actual angle, which is where the thing is hanging. Then if we want to get 40,000, we're going to have to multiply this by a number in the hundreds. So KP is going to have to be on the order of 100 to, say, 800, something in that region. Did you have a question?
I guess so. So if PID is running at like 1,000 times a second, right? Isn't that going to be like really just incrementing a lot? Like if you have like 100.
Incrementing what?
Your value for. So. I answered my own question in my head. It's okay. Yeah.
This doesn't increment an integral. It is the output. The output. There's no sort of summation after this, right?
Yeah.
So if we have a large error, 250 units, and we multiply it by around 200, then we're going to get a number around 40,000. And so the motor is going to be at full power. So this suggests that a constant in the ones or tens is going to be too small, and in the 10,000s is going to be too big. So this would be, setting it to 100 might be a good place to start. What about the first derivative? Now we have to we have to guess how fast that thing can turn. So I'm guessing, I think that this is about right. I mean, the natural period of this pendulum is around a second, but you can probably, that motor I think will generate about 3 G's acceleration or so. So you figure that the time constant is going to be something like 300 milliseconds or so. And so if that's the case, then if we rotate 250 units in, say, 0.1 second, so if we rotate 250 units in, say, 100 milliseconds, that turns out to be about 2.5 ADC units per time step. And I'm claiming that well, to make the term big enough so that it matters to the calculation, the value you get out of the differential calculation has to be something like the same size as the term you get out of the linear portion, the proportional portion. And since this term is about a factor of 100 smaller, you'd guess that the differential term has to be about a factor of 100 bigger. So this is going to be something like thousands to 10,000s. So you might start with 1,000. It's certainly not going to be 2.5. Right? It's going to be in the thousands or so. Oh, so the errors are all in fairly large integer range, 0 to 1024. The constants all have to be in a fairly large range for both these terms. That means we can just use integer arithmetic. No need for stinking fractions here. Well, not quite, because ki, the lead term on the integral, turns out has to be fairly small, because now you're taking numbers that are up in the 100 region and adding them together for a while. And so you get a fairly large number fairly quickly. So ki has to be fairly small. And what I found was that the system wasn't stable if ki was greater than about 0.5, that the integral term wasn't stable. In fact, it worked pretty good down around 1/16 or so. Oh, damn! Now we need fractions.
Well, you can just use a shifter.
Exactly. Thank you. So instead of doing any kind of fractional arithmetic, you just take the sum of the errors and you shift them 4 bits or 3 bits or however many bits you want. So it's all integer arithmetic and a couple of shifts. So you can code this up with high-speed arithmetic quite easily, which means you probably could make the interrupt service routine run faster than a millisecond. Should you? Would that be a good idea?
You don't want it running faster than the system's ability to respond to your new frequency.
That's right. Therefore, since the bandwidth of the 4n35 is about 1 kilohertz, you can't go much faster. Also, a millisecond is rather short compared to the time constant of everything else. The motor has a time constant of 20 or 50 milliseconds. The pendulum has a time constant of half a second. Milliseconds should be fast enough. So you're going to scale the numbers, assuming you're using ADC units, you're going to scale the number something like this. Let's say that instead of using ADC units, you decide to calculate everything in radians. Now, you're going to have to use fixed point arithmetic. So I suggest doing all of the calculations in raw ADC units. The resolution is as good as you're going to get because that's the measurement you can make, right? So why not do that? Don't convert it to volts, don't convert it to radians, just use the output of the ADC 0 through 1023.
How do you want us to calculate the angles we're setting, like 30 degrees?
Well, you could, since you're going to have, you could easily have where you're going to have this hooked to an oscilloscope from day one. Hold this horizontal, measure the voltage. Put it at 30 degrees using the protractor that is in the lab. Measure the voltage or measure the resistance. Or you could calculate it based on the fractional rotation. If this thing goes through full scale in 340 degrees, you can calculate how many what 30 degrees is going to be in terms of ADC units, and that's good enough. By the way, these precision potentiometers are only precise in the sense that they are linear and have low friction. The absolute value of the resistance is pathetically off. Most of them I've seen measured have been around 8.7 kiloohms. Luckily, except for measuring the 50% point of the potentiometer, you don't actually need that number. And if you wanted to set 50% using, instead of measuring the resistance with an ohm meter, you could, of course, hook up the ADC to it and turn it to 512 or 511, and you'd be at half scale. So if you end up using the absolute value of the potentiometer, you'll have to measure it because it's not guaranteed, but it's probably around 8.7 kiloohms. Any questions? So again, the very first code thing you're going to do is get the interrupt service routine running and get the display running for the motor output, for the PWM output, and the actual position. Then you can debug. But there's this cryptic line of code here. There's this cryptic line of code that says, use the first order infinite impulse response digital low pass with a time constant of about 16 PWM cycles. And then claim that you can write this filter as display equals display value plus PWM on time minus display value shifted by 4. Do you recognize that as a differential equation? Does that automatically code in your brain to being equivalent to an RC circuit? Does it? I don't know. Does it? No? Yes? No? So, the question is, why does this work? And let's start with the analog version of this, where we have V in and V, what did I call it? V out, I guess. And as we all know, C dV out dt is equal to the current through the capacitor. And as long as there's no load, then V in minus V out over R must also equal I. We set those two equal to each other, we get a differential equation. dV out dt is equal to 1 over RC times V in minus V out. And now they're almost looking similar. There's that difference term, and there's some reciprocal term here because we're dividing. So all we need to do is one more operation, and that is to discretize this and say that we have actually V out at time n minus V out at time n minus 1 over delta t, Euler approximation of the first derivative, is equal to 1 over RC times V in at time n minus V out at time n minus 1. And then we identify that when we rearrange this, that we have V out at time n, which is the value we're going to display, is equal to V out at time n minus 1 plus delta t over RC times V in n minus V out n minus 1. So now we can clearly see, that's all, I hate people would say that. What we can see here is that we have the new display is equal to the old display plus some function, and that's what we have here. The new display value is equal to the old display value plus some scaled version of the difference, just as we have here, PWM on minus display. And we have a pure number here, because RC has units of time, delta t has units of time. So this is just a pure number. And we can set it equal to 1/16. And if we did, then we would have a low-pass filter with a time constant of 16 sample times. Why did I choose 16 sample times? So 16 sample times is like 0.016 seconds. That's still pretty fast with regard to any of the dynamics of the system. But 16 samples, averaging over 16 samples, is enough to reduce a lot of the PWM noise from the calculation. So you might want to experiment with this. You might want to try shifting it 3 or 5 and see if you like it better or worse. If you shift it by too large a number, let's say 8, now you're talking about a 256-point average. That is now starting to be a quarter of a second, which is comparable to the time constant of the pendulum, and therefore will distort the output. I would say you want to be short compared to a tenth of a second. So this is a highly encoded version of the differential equation describing a RC filter. And it's a really quick and dirty way of building a digital RC filter that doesn't have to be very good. It's not optimally flat. It's not Butterworth. It's not Chebyshev. It's just fast and easy to program. So whenever you need kind of a utility low pass, you can do something like this. So what more questions now do you have on this thing? You want to talk about the control loop some more?
Yeah, if we're talking about the control loop, let's talk about the integral term.
Okay.
So what keeps you from having an integral term just build up over time so that after the system has been running for an hour, the integral term gets massive?
And overflows, and then all hell breaks loose and the system crashes. And yeah, good question. And the answer to that is that rather than just taking a simple sum of the running error, what is generally done is to take the min of some max value or the sum from zero crossing to the current time n. And I'll tell you what I mean by that in just a minute. Error n. And the zero crossing is going to be determined when the sign of error n is not equal to the sign of error n minus 1. So now, what should you set the integral to when there's a zero crossing? One possibility would be to zero it at zero crossing. Say, I've built up to 0. I'm going to zero the integral term if we go a little bit high. That'll certainly stop it from increasing anymore. But if you're getting a significant amount of your gain from that integral, when you zero it, that value that's been the angle that's been creeping up will suddenly decay again and then come back up. So at zero crossing, you might want to say that the integral is equal to, say, 0.9 of the old integral. In other words, you take whatever value it's at, multiply it by 0.9 or some fairly large fractional number, and reset the integral to that value rather than 0. In other words, you decrease it a little bit. Point 0.9, oh no, floating point arithmetic. But wait. You could make it the old integral shifted by 1, that's a half, plus the old integral shifted by 2, that's 0.75, plus the old integral shifted by 3, that's 0.825. That's pretty good. So for the cost of 3 shifts, you can multiply by 0.825. Sold. If you want to put another term in there, you can get as close to 9 as you want by doing shift operations. 0.9 as you want by doing shift operations, which are way cheaper in time than doing floating point arithmetic. Because a shift by any number of bits in this architecture is one cycle, one machine cycle.
Is the difference between multiplication time and addition time?
Say again?
Multiplication time and addition time?
Addition time is one cycle. multiplication time is 2 cycles for 16 by 16. Multiply. 32 by 32 multiply requires 4 of those. So it's 8 cycles. And a couple of adds, 3 adds. So you're going to want to think about the numerical efficiency. I don't actually know if this will run in floating point at a kilohertz. I haven't ever tried it. It didn't seem worth the trouble since it could do integer arithmetic. But I'm sure somebody will try. So you're going to calculate a PID function in the interrupt service routine. You're going to measure you're going to read the ADC. You're going to calculate a PID function. You're going to update the PWM. Then you're going to update 2 DAC channels, one for motor speed, one for angle, and one for motor speed control voltage. And then bail out. So it's going to be a very fixed routine. You have to make sure that you have to saturate the control algorithm so the PID can never go below 0, can never go above 40,000. So whenever you overshoot the angle, whenever this thing comes swinging up and goes past the controlled angle, the desired angle, the motor just shuts off. It doesn't slow down, it's just off. Goes to 0.
When you're displaying the motor control value, how do you convert from the 0 to 40,000 value that you're using for PWM to the 0 to 65,000 value that you can actually put on the DAC?
Okay, so no, you have to bother. So that's a good question. So the output of the PWM is going to be 0 to 40,000. The output of the DAC is 0 to 4096. Looks like a divide by 10 would do it. On the other hand, for the sensor, 0 to 1023 on the sensor, if you multiply by 4, then you'll get 0 to 4096. So you're going to want to multiply the sensor by 4 and divide the PWM output by about 10. The only logic that's going to be outside of the interrupt service routine is the user interface. I suggested using a simplified user interface consisting of 1 trim pot and 2 buttons to do the user interface. But if you want, you can do the keypad instead. So you have to be able to input 4 parameters: desired angle, KP, KI, KD, and at boot time, when you press reset, the system should come up with the best KP, KI, and KD set that you could come up with, and the system should run the control algorithm -90 to 0 to +30 to 0 to -30 back to 0.
Wait, so if we're doing KI in terms of a shift by some number, then how exactly are we going to be inputting that? Because it's not something that you can discretely input the same way you could input the values for KP and KP.
Okay, so let's say that you do it as a shift number. You could just say, enter the shift number, rather than the actual value. So you could say enter 0, 1, 2, 3, or 0, -1, -2, -3, and that would tell you how much it shifts. So there's kind of like you enter powers of 2. Or you could do the translation yourself, or you could do up-down keys. I suggest having a potentiometer where you select the parameter you want to mess with, then you turn the potentiometer to the new value, and then you freeze it with the other button push. But however you feel like doing it. As long as you can set the 4 parameters and read them on the TFT. Next week, starting next week, we start the final project, right? As soon as you're done with the lab next week, you're starting on the final project. There'll be a progress report due the first lab, because that's 1 week into the final project. And so you better be gearing up to start that at the same time you're finishing lab 4. I'm going to raise the limit on, I don't think I've changed the documentation yet. I'm going to raise the cost limit to $125. And the penalty, the points penalty for going above $125 is a square law. If you go $1 over, it'll cost you 1/10 of a point. If you go $10 over, it will cost you 10 points. Don't go over.
Is there a point bonus for going significantly under the limit?
There is no point bonus for going under. That would be interesting to do. I'll have to think about implementing that, because in the real world you might well be rewarded for being under budget. So I have to think about how to do that. I haven't done that before, and I won't do it this year, but I'll take that under consideration for next year. There will be a point bonus for finishing early, as explained in the Lab 5 write-up.
Consider that if you make the cost points, going under cost, your project will shift to being a lot more software and a lot less hardware.
So you're saying if points matter for being under, the amount of hardware would go down.
Yes.
That maybe is not a bad thing, if it causes you to think more.
No, but I mean your diversity of projects will decrease.
Oh, maybe. Or maybe people will get really clever about using the built-in hardware in the PIC. There's all kinds of, this is gigantic toolkit sitting in the PIC, right, of all kinds of timers and compare units and stuff and ways of hooking the units together. That'd be interesting. But I'm not going to add points for under cost right now. There's a penalty for over cost that's rather harsh by design. And anything that you own now has to be budgeted. You don't get to reuse the old RC car. I used to allow that. People started gaming it. Oh no, I bought this Arduino 5 years ago. Yeah, wait a minute. Arduinos didn't exist 5 years ago. Oh, yeah, I meant 3. So, so people were gaming the system a little bit too much. So if you could prove that you dumpster dove and found something, then I might let you not budget it. I've seen people come up with the coolest stuff out of the dumpster, including a millimeter accurate flatbed scanner made completely out of ceiling tile struts and drive screws. Unbelievable. Homemade gears, just crazy. And remember that if you pitch a project that is a collaboration with an outside lab or MEng project, that the budget is waived completely. You can spend whatever you need to spend. But that has to be approved by me and by the principal investigator on the other side of the collaboration. Yes?
Is there a cost for 3D printing or laser cutting if we choose to use RPL?
If you can get it for free, there's no problem. If you decide to cut a circuit board, if you go to expresspcb.com, you can get 3 circuit boards, 2 3/4 inches by 3 1/4 inches for $60. If you use one of them, it's $20. All right, let's hear it.
So clearly we buy like 1,000 to get a terrible discount and only use one of them, right?
All the cost is yours, you're spending. Is that really worth
No,
it?
I'm just gonna buy my way into a grade, right?
Sure, you want to get the hundreds price on the circuit boards. Go crazy. I'll talk more about constraints next time.